Welcome to AP Calculus, section 3.4. Going to get a little zoom working here, and we should be good to go. All right, this is kind of a cool spot of calculus. There's so many of them, but where we start kind of turning calculus from mechanics into real-world type problems. No sense in knowing it if we can't apply it. So, physics definitions, which we'll spend a lot of time with, probably primarily we want to be very, very good at physics definitions. That's what a big portion of what we're going to be doing on the test is about. Suppose S, and for whatever reason, S is just often used for position. Suppose S equals F of t gives the position of an object moving linearly at time t. So linearly, it's just moving back and forth across a line. That's very, very common. You'll hear the term particle moves on the x-axis or something like that, a particle. It's always about a particle. Well, hopefully we get some better real-world applications. So this gives the position. That's really critical for us to recognize position of an object moving linearly at time t. The displacement is how far the object moves. That's what displacement means. It's a vocab word. We need to be strong with that. Of that object over time is this delta symbol. This triangle is delta. That's change. Change of position equals where our position is after some time versus where it is when we started. We take time plus our change of time minus where we were. Again, these are just basically oftentimes just shown as heights. It's our height to the right where we ended versus our height where we started. Well, that makes sense. Our change in position, like if I'm moving along and just back and forth, back and forth, back and forth, I moved to here and started there, moved around a lot. I've moved all over the place, but my change in position is just this. Or if this was as a Y, if I started here and ended here, I can wiggle around all I want, but my change in position is that amount of rise, and that's what they're saying here. Average velocity. Well, shouldn't our average velocity be our distance divided by time? So that's our change of position divided by our change of time. If our change of position is this, it's this divided by change of time. That should all have a familiar look to it. That's a difference quotient. Okay, if we want to find an object's instantaneous velocity, this should look familiar. Then we set our change of time. We want it to get closer and closer and closer to zero. That's our instantaneous velocity, but that is a derivative. So what they're saying here is that velocity is our derivative of our position equation. Oh, okay, that's important to us. And it says, or simply, change of position over change of time, the derivative of position with respect to t. Velocity is directed speed, which means that positive and negative velocities indicate motion. Often up is positive velocity, down is negative, right is positive velocity, left is negative. Speed ignores direction. Therefore, speed is just the absolute value of velocity. So if I'm driving to Rockford and I say I'm going a velocity of 50 miles an hour, then my velocity returning home is negative 50, but my speed was 50 both directions. Okay, acceleration is the derivative of velocity. So what do we have? We have position, then we have velocity, which is position's derivative, and then we have acceleration, which is velocity's derivative, or position's second derivative. Okay? And that's what we've got here. Second derivative with respect to t of position, or first derivative of velocity, is acceleration. So here's the biggie. What you're going to really have to focus on is what they give you to begin with. oftentimes we're going to be given a position function, but sometimes we could be given a velocity function, and we only are one derivative away from acceleration. So really, really important we read closely on these. Gravity provides constant acceleration, and we should be familiar that that is negative 32 feet per second, which means it is accelerating at that rate, or negative 9.8 meters per second. We'll use those enough that you don't have to make a huge effort to memorize them. That would be like memorizing the ABCs. You'll do it enough, you'll have that down. All right, business definitions. Let's say we're given a function that says we have a cost of producing X units. Now, we would typically say, well, if it costs $20 to produce a unit, it might cost $20 to produce it later. Well, maybe we have some kind of scale that as time goes on throughout the day, for whatever reason, it costs us more because maybe using our air conditioning unit costs more. There's so many things that get thrown in there. So we have a variable cost of creating things. In past story problems in algebra, it might have said, well, we make chairs and it costs $15 for each chair we make and $35 for each table we make, and that was just a constant cost. But costs could definitely vary along some function. So suppose that we have a business that models the cost of producing X as C of X and the revenue as R of X. Marginal cost is the cost of producing one additional unit, and that is the derivative of the cost function. And marginal revenue, likewise, is the derivative of revenue. Okay, there are whole entire courses built on business calculus. It is a course. Okay, the graph below shows three functions: one representing the position, our position function over time; another showing velocity of that object over time; and third showing the acceleration of the object over time. Interpret the graph to decide which curve is representing each function. So there's lots of things we could look at here. We could look at like intersections perhaps, but we could also look at like maximums, relative minimums. We could look at zeros, and would encourage you to pause this. If you're taking the course, you're here for the discussion, you're in course watching this, in the class watching this video, I'm going to give you just a bit of time, but you can take as much time at home if you're watching the video as you want. Pause it and see if we can determine which of these is position, which of these is acceleration, which of these is velocity of one another. Okay. So if we're looking at these things, if I look at perhaps this maximum, I notice this maximum appears to be in line with that zero. I notice this maximum appears to be in line with zero, the maximum of C. Okay, so what would a derivative be? What would a derivative be doing? Let's take a look. Let's continue with that thought. This relative minimum of A, this minimum over here, I think I said maximum, but that relative minimum. This relative minimum of A looks to be in line with B's zero. Well, what do we know about maximums and minimums? This has a slope of zero. This has a slope of zero. This has a slope at that relative minimum of zero. So where my red slope of zero is above curve A's zero. Slope zero, position zero, slope zero, position zero, and curve A's minimum is the same with line B's zero, slope zero. All right, well, how about we continue discussing slopes? This slope is positive along C, and it looks like there's a relationship between curve C, a direct relationship, and curve A. This is positive and steep. Well, this graph is positive and big, and this graph's slope slows down as this gets closer to zero, and then this guy's slope turns negative as this guy crosses into negative territory. So this graph is modeling the slope. Take a look at this, where this graph is most negative right here. Appears like maybe where this graph is steepest down, where its slope is most negative. So graph A is modeling graph C's slope. Likewise, graph B. Slope is 0, B is 0. Slope of A positive, B is positive. Slope of A more positive, getting steeper and steeper slopes. Slope of the tangents, B is getting higher. Slope is negative on A, and B is negative. So it seems to me that C is kind of our most evolved function, and the derivative of C, it seems to me, if I call that C of x, how is C of x related to A of x? It seems as though A of x is the slope of C of x. If A of x is the slope of C of x, then C prime of x appears to be A of x. And likewise, B is to A. How would we define B of x? B of x appears to be a representation of A's slope. So how do we tie that up then? Well, this would be position, take the derivative to get speed, take the derivative to get acceleration. So I believe that C would be positional, and what do we have from there? Its derivative is A. A would be velocity. I said speed, but velocity. And B appears to be acceleration. Okay. Again, the wording is based on a positional graph, but definitely applies to other types of real-world problems. Okay, so hopefully we can look at a graph and build its derivative graph off of that. All right, let's take a look. The number of gallons of water in a tank T minutes after it started to drain is given by. Now, the number of gallons of water in a tank is given by this after T minutes. So we've got gallons we're working with minutes. That somewhere along the line we're going to talk about gallons per minute, but this is just gallons. This is an amount. This is not a rate yet. And it started to drain is given by this function. Thanks. How fast is the water draining at the end of 5 minutes? How fast is it draining? That is the rate. So we got to make sure. This is like our position function. It's our amount we've accumulated. Now we're looking for a rate. So we need, how fast is it draining? We need Q prime of T. Q prime of T, if I have this function, 250 times 15 minus T squared, we could use a difference quotient here, or find this derivative with limits, but I need this guy's derivative. We could FOIL this. We could chain rule this guy. Now, realize that's, if you're following along in the book, that's something we haven't gotten to, but there's a lot of ways to find the derivative of this. I'm going to chain rule this, and the chain rule would be, I'm going to take 2, I've got an inside function, I've got an outside function, which is 250x squared. I'm going to take 2, bring it out in front, I get 500 times 15 minus t to the first, and then multiply by the inside derivative, or treat the mother function, 500 something to the first, treat the baby function, derivative of 15 minus t is negative 1. So we get negative 500 times 15 minus t. That is our rate. Now, we got to have words with that. We got to have units. How fast is it draining? We're working with gallons and minutes. That is gallons per minute. That's how fast it's draining. What is the average rate at which the water flows out during the first 5 minutes? Well, that's a completely different question. I need to know how many gallons flowed out in 5 minutes and divide that by 5. So that is how many gallons? That's not a rate anymore. That is Q of 5 minus Q of 0. That's what we ended up with, over 5. So that is 250 times 15 minus 5 squared minus Q of 0, 250 times 15 squared, 15 minus 0 squared, all on 5. Or 250 times 100, that was easy, minus 250 times 225, all on 5. And I'm going to be lazy here and go to calculator. We've got 2,500 minus 250 times 225. Could have reduced some first. I've got negative 31,250 on 5, or negative 6250. That is our average. So what are we looking for? What is the average rate? It's rate. Our average rate is that many gallons per minute. Okay? Kind of ran myself into a corner there. All right, example 2. There we got our particle. We talked about we're going to have particles moving around all over the place. The particle moves along the x-axis so that at any time t is greater than or equal to 0, the particle's position is given by this. Sneaky suspicion that may come back to be a factor here. At any time where t is greater than or equal to 0, the particle's position is given by this. So at 3, let's see, do we ever introduce anything to do with time here? Let's just say time is in seconds for right now, and let's say moves along, let's say our position is in feet, just so we can give unit measures. We'll typically have that information will be given. Find the velocity of the particle. Well, first let's find out what we're dealing with here. The particle moves along, so it's position. This is our position function. Velocity is just the first derivative. So I need dx dt, or I need x prime of t. That, of course, is 3t squared minus 12. That's our velocity of the particle at any time t, and our velocity would be in feet per second. Okay? Just a reminder here for us that is our velocity. Find the acceleration. Well, acceleration, so if I go velocity of t equals x prime of t, I think they're using x because it's along the x-axis. So velocity of t, to get to acceleration at time t is equal to velocity's derivative. Oh, this is easy. 6t, derivative of 12, 0. That would be feet per second squared. Just kind of a reminder. Find all values of t for which the particle is at rest. So now we got to think a little bit. Particle is at rest when what? When its position is 0, when its velocity is 0, or when its acceleration is 0. And the one most likely to trick people is, oh, when its acceleration is 0. No, think of cruise control. If you're going 55 miles per hour down the highway and you're going on cruise control at 55 miles per hour, you're not accelerating, you're not decelerating. Okay? So when acceleration is 0, you continue at 55. You're not at rest. I mean, you hit a squirrel at 55 miles an hour. Don't tell that squirrel you were at rest. Find all values for which the particle is at rest. The particle is at rest when the velocity is 0. So we want velocity to be 0. At rest when velocity is equal to 0. Is that all right? So when is velocity equal to 0? Well, here's our velocity function up here. Therefore, 3t squared minus 12 equals 0. And those are helpful things to have on your, when you take an AP test, helpful to put that information down there. So we get, as we solve this guy, t squared equals 4, so t wants to equal plus or minus 2, but sure enough, t just equals 2 as t is greater than or equal to 0. Okay, anywhere you can put some little words in to help explain. Let's get in good habits here. Find the speed of the particle when its acceleration is 0. We're going to find the speed when acceleration is 0. So, what are we going to find first? We need to find when the acceleration is 0. So I want to say acceleration is 6t, and we want that to be 0. Oh, well, that happens when t equals 0. Find the speed when t equals 0. Our speed is our absolute value of our velocity. And our velocity at 0 is 3 times 0 squared minus 12, negative 12. So that would be, we want the absolute value. Speed is absolute value of velocity. So our speed at t would be positive 12. Maybe absolute value of negative 12 or positive 12. Positive 12 what? Well, I put in feet in seconds, so feet per second. Time 2, what would that be? That would be seconds. Is the particle moving toward or away from the origin at t equals 3? Well, what do we need to do? What do we need to know? We know it's moving along the x-axis, so it could be moving, okay, at time 3, toward or away. It could be to the right here, moving toward it. It could be to the right and moving this way. It could be to the left and moving toward it. It could be to the left and moving away from the origin. So we need to know where we're located at. We're going to find the position at t equals 3 seconds. Therefore, our position function is x of t, or x of 3 in this case, is 3 cubed minus 12 times, not t, times 3 plus 5, or 27 minus 36 plus 5, or 32. This is at negative 4. So I'm at negative 4, so I am over from the origin. I'm over here. So is the particle moving away? Now I need to know which direction I'm moving. Will position tell me that? Maybe if I put in position at 3.0000001 and figure out what direction I'm going after 3 seconds or right before, but maybe I make a change in directions in those times. I need to know my velocity at this point, whether my velocity is positive or whether my velocity is negative. So let's find velocity at 3. Velocity at 3 is 3 times 3 squared minus 12, or 27 minus 12, or 15 feet per second. Since we are left of, I shouldn't probably say we, since the particle is to the left of the origin at 3 seconds and is moving right at 3 seconds, we, or the particle, are approaching the origin. Okay. The more I look at tests, the more you need to write to explain answers, and that makes sense in a real-world environment. Okay, the graph below shows velocity of an object moving on a linear path. When does the object reverse directions? Here's the biggie. We're going to look at graphs like this, and if we're not careful, we're going to say, oh, its position. This is its position, but this is its velocity. its velocity is 3, its velocity is 2, its velocity is 1, its velocity is 0, its velocity is -1. I just went at 1, I have velocity 0. It looks like moving down, but we're really moving to the right, but not to the right because I'm moving over to the right, because right now I'm moving to the left. I'm moving with a velocity of negative here. That is movement to the left. So, when does the object reverse directions? When I go from having a positive velocity, moving forward, to have a negative velocity, moving backwards. At t equals, and let's say we're dealing in seconds again, at 1 second. But also, let's see, I'm moving, the velocity is shown here. The velocity is negative, the velocity is negative. The velocity is still negative here. The velocity is still negative here. Still negative, still negative, still negative. Now the velocity is 0, and I go from velocity being negative to velocity being positive. I go from moving to the left to moving to the right at 8. At 1 and 8 seconds. Approximately, when is the object moving at a constant speed? I'm moving at a velocity of 3, not 3 anymore, not 3 anymore. I'm moving at a constant speed of -1 here, at -1 here, at -1 here, at -1 here. It looks like approximately when is the object moving at a constant speed for time equals, or let's say if it's in seconds, from 4 to 6 seconds. You could say from 4 to 6 seconds if we're dealing in seconds here. Again, you're typically going to be given a unit to discuss. Graph the object's speed from 0 is less than or equal to t is less than or equal to 10. So I'm going to cheat here on this and just bump this graph, hold this graph up a little bit here so I can see both in the same viewing window. See if I regret that later. So I'm supposed to graph the speed. Well, how does speed relate to velocity? Here my velocity is 3. Here my velocity is -2. Here my velocity is -1. But speeds are always positive. So basically, I want everything from 1 to 8 to be flipped over the x-axis, because speed is the absolute value of it. And the absolute value of 3 is 3, and the absolute value of 2 is 2, and the absolute value of 1 is 1, and the absolute value of 0 is 0. But the absolute value of -1 is +1. So I'm going to look at this point that's at 2, -3 here. It should reflect to 2, 3. But the graph should look the same from 3 down to 1, and then we reflect up to here. And then I'm going to look at this point, 4, -1 should reflect to 4, +1. And 6, -1 should reflect to 6, +1. And 8, 0 would stay at 8, 0. And 10, 1, it appears, 10, 1 would stay at 10, 1. It doesn't reflect. So this portion right through here was reflected because it was negative. We want the absolute value of. Okay? Graph the object's acceleration where defined. Let's take a look. Just following along. I got to fold this guy up to here. Keep my graph just for a minute here. All right, acceleration. This is my velocity. My velocity is -3, and now my velocity is -2. And now my velocity is 0. Graph the object's acceleration where defined. My velocity. Acceleration is the derivative of velocity. Well, the derivative of velocity is the slope of velocity. And what is the slope of velocity from 3 all the way down to 2? It appears that it's down 3 over 1, down 3 over 1. It looks like it's just -3 from 0 to 2. From 0 to 2, we have a velocity of -3. And then let's take a look. from looks like I go from -3, 2, up 2 over 2. It looks like it has a velocity of +1. From 2 to 4, we're along a line with slope +1. Got a little bit off skew. And then from 4 to 6, our velocity is constant. That's no acceleration. Slope 0. And then it appears that we have a slope up 1 over 2 from 6 into 10. Up 1 over 2 is 1/2 from 6 over to 10. Hopefully that appears to be at 1/2. All right. So definitely not hard, but it's just we're using parts of our brain we haven't used before. Should be fine. Okay. Example 4, suppose it costs. Here we have a cost function. Notice, we're creating radiators here, and to create one radiator is probably not the same cost as creating 2 radiators and 3 radiators, etc. So we got to be concerned with at some point it's costing us too much for radiators. Your company earns this for selling them. Your shop currently produces 10 radiators per day. Find the marginal cost. All right, let's go back. Marginal cost is the derivative of cost. So marginal cost equals C prime of x, which, oh, that's a breeze now. 3x squared minus 12x, 15 gets absorbed. Okay. What's our marginal cost? Well, our marginal cost is producing those 10 radiators is C prime of 10, which is 3 times 10 squared minus 12 times 10, which is 300 minus 120, or $180 is our marginal cost, our cost for our next radiator. Our marginal revenue is 3x squared minus 6x, so our revenue for the next one is 3 times 10 squared minus 6 times 10, or 300 minus 60, or $240. Okay, so if you are working at this company, do you want to produce more radiators at a cost of $180 and a revenue of, do I have that right? And a revenue of $240. It's probably okay at that point. Did we do all that right? Let's take a look. 300 minus 120, 180. We've got 300 minus 60, 240. I believe we're in pretty good shape there. So find the marginal cost and marginal revenue. Our revenue supersedes our cost. Probably still okay. If that gets switched around, probably have some problems there. Okay, there's a peek at your assignment. Sorry about my foldings. There's the beginning of section 3.5, derivatives of trig functions. That sounds pretty exciting. Just a quick preview there. And good luck to you. Stay tuned.